with each other to eventually implement the entanglement. And you can also think about my work as basically extending the Hilbert space where the cat could live or could do some interesting things across the two boxes. And this is an actual product, that's for example. So I like to think that my work has also had some real-world applications and made it better, make real cats happier in their accommodations. All right, and before I end, I would like to just give my 2 cents about how I think about what I think about the future of this field and highlight some of the really exciting developments that's been happening in our field of superconducting circuits and beyond. Okay, so how do we think about a quantum computer? I bet everybody here has their own favorite way to think about it. And for me, I would like to just think about it as a machine that operates based on the fundamental principles of quantum mechanics. And this has many advantages because now it could utilize the special features of quantum mechanics to its advantage. So, for example, one of these features is superposition, and that just means a certain quantum system can simultaneously be in 2 different states at the same time. And if you put 2 quantum systems together, 2 or more, we can have something even more powerful, and that's called entanglement. In this case, we can think about entanglement as basically the existence of some highly non-classical correlations between the red and blue system, such that I will no longer be able to capture the information stored in the entire state if I choose to study them independently. Okay, so this is a key feature of entanglement and a very important resource for quantum information processing. I will return to this topic over and over again throughout this talk. Okay, so thanks to these features, which a quantum computer will be able to take advantage of, we can have potentially many applications. So one of them is maybe exponential speedups for certain problems. And this will maybe help us, or this will help us solve some classically hard problems, such as factorizing a really large number and finding its prime factors. But more importantly, personally at least, I think the most interesting part is that a quantum computer will be able to simulate quantum mechanics itself, which is how nature intrinsically operates. And this has many applications, including development of new molecules for new drugs or for new materials. Okay, so I've told you all of these interesting applications. You say a quantum computer, great. It's obviously a really, really powerful machine with many wonderful applications. So why don't we all have one already? Right? Why is it hard? And I actually like this little cartoon here because Wally here, even though he's generally lazy for people who actually read Dilbert, he does have a point because the fact that a quantum system can simultaneously be in a state of simultaneously being in 2 different states is actually a key barrier or hurdle towards using these states successfully, if we choose not to do anything to protect them. Okay, so this brings me the topic of errors.
This is not a successful answer for a candidate for a PhD project. just to clarify.
Yeah, I thought I was going to stop here. Yes, but I would like to explain why this is not. So, so you would ask me maybe why is this not a problem for a classical computer, right? Why are we able to operate it to such good precision on compute very demanding tasks? Well, for a classical bit, is only 0 or 1, so it can only be it's purely binary. And if you imagine basically a system that can be controlled by a certain signal, since the response is purely binary, we can draw a threshold and say everything above is nominally 1, everything below is 0. And now, if I sit at a certain point and introduce a little bit of noise, the response of the system, such as a switch, will not change as a result of that. Okay, and this is a great feature, so we can suppress the errors, or rather, the errors do not hurt us as much, so we can actually do faithful classical computation. But for a quantum system, it is actually quite different because it can be 0 and 1 at the same time, and this again returns to the topic of superposition. So now, if we want to visualize it, we can no longer just think about a control signal and a certain linear response. We have to think about it on a 3-dimensional sphere where a quantum state can be described by a certain point on the surface of this block sphere. Okay, and it can be parameterized by two angles, theta and phi. And we do have the tools to move this point around the sphere using quantum gates. However, if a small error occurs and shifts this point to a different place on the sphere, on the surface of the sphere, the resulting theta and phi will now be different, and the information that we tried to use is now corrupted. So if we use this to do computation, then we're going to get a bogus answer. So this leads us to conclude that if we want to do faithful quantum computation, we need to implement error correction so that our individual quantum systems can be protected against environmental noise. Okay, and so now we're on to the topic of quantum error correction, and we have to think about how can we actually approach this challenge. There are many different ways, and here I'm just naming two of the common examples. This is a steam code consisting of 7 qubits and 6 ancillary nodes, and it's a surface code that uses topological properties to protect quantum systems from noise. And without knowing any details about them, you can already see that the common feature is redundancy in both cases. Right? In the steam code, we're spreading 1 bit of quantum information into 7 different subsystems, and here we're breaking it down into even more systems. And these approaches usually suffer from a large hardware overhead because of the requirement of so many number of subsystems that makes up one protected quantum bit. Okay, so, but we do need to achieve this redundancy in order to prevent errors from happening or correct errors. And here at Yale, we actually choose a different way of achieving this. So this is a picture of a Wigner function of a four-legged cat state. And it's part of a larger class of bosonic codes that basically encodes information using many levels, many energy levels of a single system. And we do actually conveniently have a system that has this feature, which is just a simple harmonic oscillator where it has many evenly spaced energy levels, and we can use them to potentially achieve this redundancy. And this is a great feature, a great tool, because the large Hilbert space is perfect for this purpose, but also it simplifies the task of implementing quantum error correction. We usually highlight 2 main features, and one of them is hardware efficiency, which means that since we're using many levels of a single system, we only have one dominant error channel which we need to protect against. And over the past few years, we've also achieved extremely good coherence times for such superconducting cavities, which makes this even more appealing as a medium to store information and protect them against environmental noise. Okay, and this will be the topic that I'll focus on for the rest of the talk. So I've talked about basically our systems very generically in a very abstract way. So let's look at exactly what they are physically. Circuit quantum electrodynamics is the framework where we describe our systems. And it may sound like a mouthful, but it actually just is a framework where we describe the interaction between a linear mode, which could be a resonator, as well as a non-linear mode, which could be an atom, which could be an artificial atom, and typically we use the transmon in our experiments. For the linear mode, we can represent it as an LC oscillator, and it will have potentials like this where the energy levels are just evenly spaced, and we have access to all of them. There are many advantages of these superconducting LC circuits. Just to list some examples, because they're superconducting, they're low dissipation, and the Hamiltonian of the system is extremely simple, so we can simulate it and predict it and control the behavior by simply manipulating some macroscopic variables such as capacitance and inductance. So that's very nice, but because of these evenly spaced energy levels, we don't have the ability to individually address them, so we can't really use them alone to store or protect quantum information. In order to be able to do that, we'll need to introduce some nonlinearity. And nonlinearity for us is actually surprisingly simple. We can just use the Josephson junction, which is represented by this box. It basically shifts the quadratic potential to a cosine potential. And now the first few levels are no longer, the energy levels are no longer evenly spaced, and we can independently address either the GE or EF transition or even higher levels. And there are many other attractive things about the Josephson junction. It's the lossless quantum nonlinear element. It has a pretty large nonlinearity that we can engineer and control and design to suit the purpose of a particular experiment. So that's very handy. It's also very easy to fabricate. It's only a tri-layer process that we can just do in-house here at Yale. Non-linear tri-layer. So now we have these two great components. To put them together, we can just introduce a single capacitive coupling. And now we have a great system where we have a large number of energy levels that we can tap into, and that they can be controlled efficiently by a simple nonlinear system. In real life, this is what they want. In cartoon real life, this is what they want. So this is the superconducting cavity. This is the transmon that we use to basically just highlight the junction. The strip of metal is another resonator that also couples the transmon for a readout purpose. And this tool, this package itself is extremely versatile and offers all the tools that we need to implement control and measurement of states stored in our long-lived superconducting cavity. Okay? The T Hamiltonian that gives us these great tools is the dispersive Hamiltonian. You can think about it as a shift of the frequency of one of the modes, for example, the cavity, that depends on the mode of the nonlinear system. Or you can think about it the other way, that the nonlinear system has a different transition frequency depending on the photon number in the linear mode. Okay, so the first feature that we'll exploit is this shift of the transmon frequency. The shift of the resonator frequency as a function of the transmon state. And this is great because by measuring the frequency of this mode, we can now determine efficiently whether we're in the ground or excited state of the nonlinear system. And usually a typical readout histogram looks like this, where we can this is plotted in the log scale, so we can very efficiently differentiate if we're in the ground or excited state of the transmon by simply accumulating single-shot readouts of the from the linear resonator, from the strip line resonator. The other feature that I mentioned is the shift of the transmon frequency as a function of photon numbers in the storage cavity here. And this is extremely useful because it provides us conditional manipulations on the cavity simply using this as the ancilla. For example, using this tool, we're able to prepare some exotic quantum states that look like this. In this case, it's the superposition of the 0, 2, and 4 photon number peaks. And what I'm showing here is a Wigner function of the cavity. And you can see and this is real data, and you can see that the quality of control is extremely good in such systems. But you may ask, how do you exactly accumulate all these nice Wigner functions? So that's, again, another tool that's provided to us by the dispersive Hamiltonian. And we can think about, if we think of the Wigner function as essentially a measurement of parity after displacement to various points in the IQ space of the cavity mode, then we can essentially think about each point as a parity measurement. And each parity measurement can be done using this Hamiltonian simply by allowing the system to evolve after a certain displacement. And after the right amount of time, you see that all the different photon number states will line up, and they can be mapped onto the ground or excited state of the nonlinear system. So using this tool, we can very efficiently measure the entire state of the cavity here by probing its Wigner function. Okay, so this is a powerful tool actually, and we've used it to achieve many remarkable experimental progress. Basically, if we think about this roadmap that Michelle and Rob developed a few years ago, we've worked beyond we're continually improving our physical systems, but we're now actually able to tackle this area of the letter using the system I've just described and the tools given to us by the Hamilton. Okay, and there are actually quite a lot of really amazing work that this is not an exhaustive list, but I would like to highlight it because there's a really nice parallel between the single cavity progress and the multiple cavity progress. Okay? So we started with state creation, where we're able to prepare such exotic quantum states in superconducting cavities and do tomography on them. And then we moved on to study how to measure their syndrome, which is parity, continuously. There's been many demonstrations of universal gate sets on single and cobit qubits, and more recently we've also done actually error correction on such a system to really demonstrate the potential of our approach. Okay. So with all these progress and the techniques that we've developed, we're now well equipped to go to the next challenge, and this is really where my work fits in. Okay, so there's quite a nice parallel here because we also started from state creation when we developed the multi-cavity approach, and it's a really useful tool to show us how well we can control multiple cavities at the same time and how well we can learn about their features efficiently. And then we moved on to think about how to do gates between them and engineer some interactions. For example, we've thought about 2 ways to do entangling operations, and along the way we also managed to study interference between the 2 bosonic nodes as a really interesting demonstration of how these systems are both great tools towards quantum information processing, but also excellent platforms to study fundamental features of quantum mechanics. Okay, so unfortunately I won't be able to highlight, explain in detail all of these experiments, but I'll highlight 3 of them and hopefully convince you that indeed these operations are extremely useful. Okay, so before we go on to the details of the experiment, I'd like to just show what the system looked like. I think on the cover image, it's more of an artist's interpretation of the system, but this is the actual device. It's just a block of high purity aluminum with features drilled, 2 cylindrical features drilled into them. There's a tunnel also machined in between, such that we can insert a sample containing the nonlinear element in it. And it looks like this from the top. Basically, Alice and Bob is what we call the 2 cavities, and the chip contains the Y-shaped transform. The 2 antennas provide simultaneous dispersive coupling to both Alice and Bob. And this is the strip line resonator that provides us quick and efficient data about the transform state. Okay. So this package itself actually already provides, or this transmog, single transmog itself actually provides universal control over both Alice and Bob already. We also make sure that the 2 cavities do not talk to each other without us telling them to do so. And this is achieved by tuning them so that we can really ensure the states stay localized within each node. So in the later iteration, we also introduced additional transmogs on the side, and their purpose is to provide fast single-mode control so that we can prepare even more complex states and bring out these cavities independently for, I guess, more experimental complexity. Okay, so this is basically the playground where all the experiments will take place. So let's talk about the first experiment, where we started by trying to create and characterize a 2-mode and 2-mode cat state. And this may not mean very much to you, and hopefully by the end of it, you know what I mean by a 2-mode cat state. So we actually got our inspiration from straight out of the textbook. In this section, Hiroshi and Ramon actually wrote that the fields of spatially separated cavities can be entangled, but in interaction with an atom. And this situation could lead to really interesting non-local flavor of cat states. And when we read this, it was extremely exciting because this is exactly what we have. We have 2 cavities interacting via not a real atom, but an artificial atom. I think at that point they have yet implemented experiments, so caught up a little bit on that. Yes, but this state mathematically would look like this and I'm ignoring the normalization factor here just for the simplicity of the display. So it's an interesting state. It's very similar to the entangled state I showed earlier, where you can have two states both having the same sign in one part and the opposite signs in the other. And another feature of the state is that it is an eigenstate of the join parity operator. So this is different from what we've talked about, where we can measure the individual cavity surfaces, individual parity of the cavity. In this case, the question we ask is not how many photons one cavity has or the other, but rather what is the parity of the total photon numbers in Alice and Bob combined. Okay, so that's a key feature that will come into play when we try to characterize this state. But in our system, we can just basically think about our cavities as two closed boxes. They are well isolated from the environment, and there is a nonlinear element that weakly couples to them. But essentially, we have to put the state into the two cavities and somehow learn about its properties. Okay, so that's not a very easy task, but there is a great way to do it thanks to the theory proposal in 2013. And I'll walk you through that in hopefully a simple way. What we do, let me just go over this in a little bit more detail. Here I've prepared the circuit diagram, and here is the phase space of Alice and Bob corresponding to each steps in the sequence. The color corresponds to the transmon state either in G or E. Okay, so to start with, we have the general initial state where Alice and Bob are both in vacuum, and the transmon starts in G. And we can simply do a parallel 2 rotation such that now the transmon is in a superposition of its ground and its steady state. This is followed by a coherent displacement along a certain axis in both cavities. And after this, the dispersive interaction takes over, and the block corresponding to the transmon E will now evolve at a certain rate corresponding to the coupling between the transmon and the cavity. After a certain amount of time, and here for simplicity, I'm assuming that the coupling rate is similar or is identical here, they will both evolve to a certain to gain a certain phase. And we can just do a second displacement, and now you can see that the block corresponding to the transmon E is centered in the vacuum or the origin. And this is great because now we can just do a simple pulse that flips the transmon if the cavity is in vacuum to disentangle the transmon state from the rest of the system. And we do so by this conditional pulse, which indeed flips the transmon state, but only on this block. And we do a final symmetrization to displace everything back such that they are symmetric about the origin. So this is a pretty simple sequence, but it's a deterministic way to create a really complicated entangled state. And you can think about this as now this block is corresponding to this one, and this one to that. Okay? And you can also think about it as the sign being correlated. They're either both plus or both minus. Okay, so now I've basically told you I've created state, but how do I show that I've done that? Okay. Let's just have a look at this property again. The join parity is a useful operator for us in this case. And we can study the full feature of the state just as a single Wigner contains the full feature of a single cavity node. The join parity of the join Wigner will contain the full information of this node. However, now it's a 2-mode state, so it lives in a 4-dimensional phase space. So that is a large dimensionality for general measurement, and we need to be able to cleverly pick certain planes in order to really capture the features without spending months to take data. Right? So the key thing before we actually look at the data is now in these two boxes we have an entangled state. And if I just open one of them, I should not be able to get any useful information. I would have destroyed the quantum correlations between them. If I open the other, the same thing should happen. So I need to open both of them, and now I can think about I have a cat that's fully alive and playful, and that can correspond to these two states. Okay, and if I do that again, maybe I'll get a different kind of cat, and now they correspond to that.
Oh, they were cuter when they were alive.
They're just sleeping.
Okay.
Very sound. Thank you.
Okay, so the data looks just as good, I promise you. All right, so basically the key message I want to express is really, in order to study an entangled system, we must look at it as a whole rather than study them independently. And now, let's see. If we do study them as a whole, we can run a simulation and see and get what we should expect. Okay? And this is a cut around the real plane of the two-mode system, the two-mode entangled PET state. And we can see that these two blocks correspond to the photon number distribution, which is basically at either plus alpha or minus alpha. That makes sense. So we can also look at the center, and this means right here it has well-defined joint parity, which is what we expect. And on the orthogonal plane spanned by the two imaginary axes, we see that there are only fringes. And you can think of these as the whiskers of a cat, because that really contains all the Hahn coherence of the system. Okay? And knowing what we should expect, we went around and actually collect the data. And thanks to the amazing software and hardware development that we've had over the years, we're able to accumulate a large number of data, and they really reproduce all the features exactly. Okay? In both planes, you can see that we have very good qualitative agreement. We can even zoom in and look at the fringes carefully, and we see that they're very much in agreement, maybe except a small reduction in the overall contrast of the features. Okay, and to do this more carefully, we can even try to do so in 4D, but in a clever way. So now I'm transversing along the fringes, so you can see that the two blocks corresponding to the classical correlations do not change in color, but the center one goes up and down between blue and red as it oscillates in correspondence to the color of the fringes. All right, so now we've looked at the system as a whole, and let's see if we're wishful and we really just do want to open one box at each time. And this is what we observe. There are no more fringes between them. Right? There's only classical correlations, and you can see this is a statistical mixture in both Alice and Bob. Okay, so this really reinforces the concept that when you have an entangled state like this, you can't express them as two separate kinds. Okay, and to complete the picture of our understanding of this exotic state, we can study its behavior in the time domain as well. So we can go back to the imaginary plane and really just monitor the joint parity, which is the center of this plot, over time. Okay? So this from this experiment, we can learn about how the PET state evolves as a function of time, or what kind of decoherence mechanisms will hurt its quantum coherence. And if we do so, this is what we see. We see an exponential decay over a few hundred microseconds. And if we fit a decay constant to it, it's roughly about 150 microseconds. And we can understand this by simply considering the single photon loss rates from each cavity. So in other words, what we're experiencing here, or the reason why we're losing coherence or the tightness of the state, is because the cavities are losing photons. Even though they're long-lived, they're still losing photons at a certain rate. And just to put this number into perspective, I think they're comparable, if not slightly better, than many of the state-of-the-art transmon two-level systems. So this really also echoes the motivation of us, our motivation of putting our quantum states in superconducting cavities rather than two-level systems.
Can you say something about how long it took to make this?
How long? The preparation time is on the order of a few microseconds. So there are two selective passes, about 4 or 5 microseconds. N bar is no, alpha is 1.9 here, so N bar is about 2. Okay.
You're pretty much dominated here by the worst cavity.
Yes, they're actually they're both relatively long-lived, but yes. Yep. So that concludes the first experiment where I've told you the state preparation and measurement of an exotic quantum state in two cavities. And this brings me to the next part of the talk. And now I want to move on to actually think about how to make the two cavities talk to each other in a way that I can control and that'll be useful to me. And this leads to the implementation of a tunable coupling between the two nodes. Okay? And when we're deciding what we want to do, which exact coupling we want to implement, we actually got some inspiration from the optics community, where we can essentially use cascaded interferometers as quantum processors. And such system would typically require the preparation of quantum states, beam splitters, differential phase shifters, as well as detection of the final output state. And in our circuit QED system, we already have really robust preparation of states. We also have phase control thanks to dispersive Hamiltonian. We do have good detection, I've shown you, either by parity or photon number measurements. The only thing that's missing right now seems to be the beam splitter. So we went ahead and tried to see if we could actually engineer a beam splitter interaction between two cavities that are tuned from each other. And just to emphasize this point, that if you have two modes that have very different frequencies, they normally do not mix with each other. So in order to engineer the operation, we need to borrow some ideas from prior works, some parametric processes, either the amplifiers or these two photon drives, where we can use the junction as a frequency converter. Okay, so we can put in some external drives and use that to basically convert one excitation from Alice into another excitation in Bob. And this will provide us a way to essentially turn on and off interaction between Alice and Bob, depending on what drive we put in from the outside. So that's a very handy tool, and you could go ahead and do that using this frequency matching condition. We can basically turn on and off this particular Hamiltonian. And this is a useful one. You can think about it as with a certain rate, I can create a photon in A and now one in B, or do the opposite process. Okay, the simplest experiment we can use to test this Hamiltonian is by initializing a single excitation in one of the cavities. In this case, it starts in Alice. And if we turn this on, as a function of time, we should see that the excitation goes coherently back and forth between Alice and Bob. And experimentally, we monitor the probability of P10, which is the photon actually in A and vacuum in Bob. And we see that indeed it coherently oscillates over many 100 microseconds or so. And we monitor the opposite case, where we want to know if the photon is in B and Alice is fully evacuated. We see the same oscillations, but exactly out of phase with the previous case. Okay, so this tells us a few things. One of them is that overall the photon really only stays in two modes alone, and they do not go outside phase space, because you can sum up the two oscillations. The envelope behaves exactly as the cavities would if they were left alone. Another feature is that here we've implemented a full swap operation, which on its own is a useful gate. It's a state transfer. It can also be part of a larger quantum circuit. And at half the swap time, we see that the probability of U1 or P10 and P01 are approximately equal. And this is where we've actually implemented a 50-50 beam splitter, and the photons being split between the two cavities. So now we have the beam splitter that we wanted to implement. We can also do some other operations simply by tuning how long we turn on this interaction. So it's an extremely useful Hamiltonian. I want to show that it's indeed useful for us to transfer a quantum state, for example. And to test that, we prepared Bob instead of in a Fox state. We actually prepare something that's in a superposition of 0 and 2. And you can see the coherence of the states because of negativity in the frequency. And if we pass that through a single beam splitter, we should expect some mixing between the two. But if we do that twice, we should have implemented a swap operation, and the outcome indeed corresponds to what we would expect, that this coherent, the superposition state has been fully transferred over to Alice, while Bob now is in vacuum. Okay? And in this particular implementation, the transfer efficiency between, so the overlap between the final state and initial state is on the order of 97, 98%. So this entire swap gate is relatively robust in the organic state. Okay. And now we can test the other feature, which is the beam themselves. Okay. One good way to test that is the Holomantel type of interference between two nodes. And we all know that if you put in two photons that are identical to each other, then we would expect either 0, 2, or 2, 0 as the outcome. In this case, our starting photons are not identical to each other at all. They start with a difference in frequency of almost a gigahertz, almost more than, actually more than a gigahertz. So this is really a good test of whether our beam splitter is able to fully compensate the energy difference between the two of them. And so if we put this to test, we see that the probability of measuring 1, 1 starts high because that's where we initialize the state. And it coherently oscillates between a superposition of 0, 2 and back to 1, 1 as the system passes through multiple beam splitters. And so if we draw a line here and look at the first oscillation, it tells us that indeed the probability of getting 1, 1 after a single beam splitter has dipped to 0. And we have really compensated the energy difference between the two layers that make them indistinguishable to the beam splitter itself. And this is a good way to actually get a sense of the quality of the engineering beam splitter. In this case, it's on the order of 1 to 2%. We can also look at the second beam splitter, after the outcome after the second beam splitter, where we see that 0, 2, and 2, 0 has been fully extinguished. We see only a fully refocused 1, 1 state. And this tells us that we have not only implemented the HLM interaction, but we've maintained the phase coherence, a fixed phase between 0, 2, and 2, 0, and that's why they can refocus. They can fully constructively interfere to give the 1, 1 state again. And so from this experiment, we conclude that our beam splitter is indeed quite robust, but we want to do something a bit more interesting with it. Because it's good, because it has a good fidelity, we can now concatenate multiple of them and put it into play with other tools that we have in circuit QED. Okay? And if we do so, we see that, first of all, we can initialize the system in 1, 1 again, and we see the familiar measurements going to 0, 2, and 2, 0. And if we apply a pi phase, now the state itself is anti-correlated to the Hamiltonian, which means that if we monitor it over several other beam splitters, it's no longer able to constructively interfere and get 1, 1. You remain in the state of superposition. And here we can again implement a second pi phase to reverse that anti-correlated phase between the Hamiltonian and the state. And what we observe is that again immediately it recovers the 1, 1, and if we continue monitoring, we'll see that it now returns to the dynamics of the HLM interference. Okay, so this is a great demonstration of how our beam splitters and phase control can be put together in a way that can manipulate this sort of quantum interference on demand.
Can you say how you actually make?
So we do this using the dispersive coupling from one of the ancillas to the cavity. So we excite it for a period of pi or pi and put back.
That you have these extra ancilla,
yes.
You put a pi pulse on that.
Yes, we put a pi pulse and then let it evolve and bring it back to ground state again. So this is relatively fast. That's why it's not visible on the scale. It's about 400 or 500 nanoseconds, and on the scale that it seems rather instantaneous that it changed phase.
So the slight oscillations that you still see are sort of a miscalculation on the timing.
So you're talking about the oscillations like here?
There is still, you see, yeah, well, I guess there is also vertical oscillation, but even horizontally within the green, you can see the yellow goes away and then comes back.
I see. Yes, so it could be a little bit of the actual phase if it's not exactly pi.
And which is coming from the timing.
It's possible, yes. Yes. Okay, so this is how we can put together a cascaded interferometer, and you can already see that this looks rather similar to the cases in linear optics I've shown earlier, that you put together a series of beam splitters and phase shifters, and that in itself acts as a linear optical quantum processor.